Hi, I'm Jenna Larson, and this is my video for Lab 3 of Physics 2212, where we'll be looking at circuits. So the purpose of this lab was to predict the behavior of circuits containing resistors in both series and parallel, and then we used an online simulation, the Circuit Construction Kit by FET Colorado, I believe, to measure the values of conventional current and potential differences. And then we also examined the behavior of ohmic capacitors and resistors. And just a little results preview, we found our current to be 0.02 amps, and we got a time constant of 6.0024. Here are the three main physics principles that we'll be looking at in today's lab. The first is Ohm's law, which regards the current going through a conductor between 2 points. And then we also have the loop and node rules, which can both be seen on the screen there. And the loop rule basically says that the sum of all electric potential differences throughout the loop is 0. And the node rule states that for any circuit in steady state, the current entering a node is equal to the current leaving a node. So for the first part of this experiment, I set up a circuit in the simulation like the one we see on the right side of the screen here. And then we predicted that the ammeters would both read 0.02 amps. And as you can see, per the simulation, that was indeed what they read. And then when we reversed the connection of one of them, in the simulation, there was no difference, but I know in real life, the sign would have been reversed. For the next part, I removed the first ammeter and replaced it with a voltmeter, and the ammeter read 0 amps while the voltmeter read 3 volts, and we can see why on the bottom of the screen here. After making those observations, I went ahead and closed the circuit and used the voltmeter to measure the potential differences across various points throughout the circuit, and those can be seen on the diagram on the right side of the screen. And here is the completed graph that kind of takes the data we saw on the last slide and puts it into graphical form. And then just to, certify that the loop rule does in fact apply here, we made sure that all the potential differences did in fact add up to 0. And they did, which means that our circuit is ideal. For the next part of the experiment, I added a second ammeter in parallel with our 100 ohms resistor. And once I added that, I observed that both of the ammeters read 0.06 amps as opposed to the 0.02 amps from previously. And this is likely due to the current choosing to travel the path of least resistance. And since ammeters in this ideal scenario or simulation, they have no resistance as opposed to the 100 ohms of resistance they would encounter on the resistor, they chose to go through the ammeter where nothing is impeding them. And then on the bottom left side of the screen, you can see where I calculated the resistances of the various elements of the circuit. For the second part of this experiment, I created a small circuit with a 10 ohm bulb, a 9 volt battery, and a 0.2 Faraday capacitor. And then after I allowed the capacitor to charge, I removed the battery from the circuit and allowed the capacitor to discharge, both times observing the light discharging from the bulb. And then I made those observations, and then the times that it took the capacitor to charge and discharge can be seen on the bottom of the screen here. For the next part of the experiment, I created a circuit similar to the one on the last slide, but this time with a 30 ohm bulb. And then I recorded the various potential differences across about 20 seconds, and then used that to create this pretty nifty linearization graph down here on the left side of the screen. And then also this gave us our slope, which we will use to calculate our RC value on the next slide. Now, as promised, this is where we pull in that slope to calculate our RC value or our time constant, and then that is pretty darn close to the one that we would have expected had we calculated straight from the ideal. And we got a % error of 0.04, which is pretty darn good. And just some potential errors. I don't think there was any bugs in the simulation, but if I'd gotten some weird data, that could have been a possibility. And then obviously, I'm not a god, I'm not perfect. I know my stopwatch technique is not the best in the world, so there's definitely probably a little bit of error there as well. And lastly, just some questions to close us out. If I'd used a real ammeter in this situation, like in real life, this sign would have changed when the connection flipped. Also, real ammeters do possess some resistance, so that would have definitely decreased the current as well. And then if I'd used a real battery, in the ideal model, the capacitor would reach full charge almost instantly, but real wires do have some resistance, so that would have slowed it down a little bit, not significantly though. All right, that is all. Thank you.